So in this lecture we are going to finally define differential one forms. So the definition for a differential one form would be the following. So this is the definition. It says that a differential one form let's call the differential one form as alpha on a manifold Rn is a linear functional on the set of the tangent vectors to the manifold Rn. On the set of the tangent vectors on the manifold Rn. This means that on each point, let's say P, on each point, let's call that point as P, of manifold Rn, alpha is such a mapping that acts on the vectors on the tangent plane of the n-dimensional manifold and maps those elements of the tangent space, that means the tangent vectors, to a real number. So this is the definition of a differential one form that we are denoting with alpha, and we will see what alphas look like actually in a few minutes. But in addition to this definition, alpha will also satisfy the following. Number one is a linear property. Let's say you have two elements V and W at some point P of the tangent space. So alpha acting on VP and WP would be equal to alpha acting on VP and some alpha acting on WP separately. This is the linearity property. And then the second property will be the following, that is property number 2. Let me erase that. This property number 2 is similar to a scalar multiplication, that is alpha acting on some A and the vector where A belongs to real number will be just pulling out the A. That means this will be equal to pulling out the A outside and multiply the result that is coming from alpha acting over VP. And here, for completeness, we again say that A belongs to R, VP, WP belongs to the tangent space at that particular point of that manifold. So this is the definition. Now, if you recall from our previous lectures that whenever we talk about a vector space, we also have to discuss about its dual vector space as well. So let me give a very brief review of what a dual space is. So this is a brief review. About dual spaces or dual vector spaces. So dual vector space is something that also contains vectors as well, but when you take an element from the dual space and you act those vectors on the vectors that are on the tangent space of it, you should get a real number. This is how dual space is defined. That means, let's say you have a tangent space denoted by this. This is our tangent space. Then T star P of M is the dual space of TP M. A very simple example or a heuristic example will be something like this. So let's say you have a vector v1 by 1 2 3 written as a column vector. So this thing belongs to TP of M. What is v superscript 1? That belongs to TP star of M. So since we are only dealing with real numbers, we won't have to go into the complications of doing complex conjugates, but in general v subscript 1 will be written as a transposition and then complex conjugation of v1 itself, and this is denoted with a dagger. So this dagger sign means that all the elements of v1 will first get complex conjugated and then you have to make a transpose of it. Since we are not dealing with complex numbers, you can for now ignore this star symbol, what this star symbol means, and then since v1 is written as 1 to 3, and if you make a transpose of it, you should get a row vector, right? So v of superscript of 1 will be just 1 2 3. This is a very simple example of a dual space, and if you now multiply this thing, you should get a 1 square plus 2 square plus 3 square, which is just a real number. Okay, now from our previous lectures we saw that the Cartesian basis vectors, these were equal to this differential operators, right? So now the idea comes that since these are elements of vector spaces, these are also elements of vector spaces, right? So how do you find the elements of these vectors onto the dual space? And note that the dual space is sometimes also referred to as a cotangent space. So this is another remark. Dual spaces are also known as cotangent spaces. And all this subscript and superscript things are related with some covariant and contravariant stuff, but I won't go into that because that is a part of tensor analysis, which is not our topic here. So we'll stick to the notion of dual spaces and tangent spaces, or so to say cotangent spaces. So our goal is to find the dual elements, that means the dual basis elements of these operators, and we write the dual elements or dual version of these operators as following. This is the dual version. This we can write it as dx1, dx2 and dx3. And you might say, okay, these dx's are something you learn as differential in a calculus course, or this is the thing that you have seen in your first 4 weeks, and we'll get to that we are calling this thing a form, we'll call it a one form, but also we are calling it as a differential, and how these two ideas relate, we'll get into that. Okay, so for the partial derivative with respect to x1 coordinate, it will have a dual element as dx1, such that dx1, when acting upon this operator, will give you a 1. However, if you act dx2 on dx3, you should get a 0. So in a more compact notation, you can write this multiplication that we defined at the very beginning of the lecture, that in the definition of one form is that dxi dx of j will be equals to delta ij, and this is known as the Kronecker delta. What does Kronecker delta mean? Kronecker delta is just an identity matrix. So Kronecker delta is 1 when I equals to j, and the value is 0 when I not equals to j. This is just a compact way of writing things. So finally, we see that our differential one forms for a three-dimensional Cartesian coordinate or a three-dimensional Cartesian vector space will be the following. One form for R3 is the set dx1, dx2, dx3. Another hand-waving way of knowing that this is indeed a form is to show is to count that how many d's are there. That means you have some variables or coordinates and how many d's are there. So it has only one d, so people call it a one form or a differential one form. But there's just a hand-waving way of remembering things, not the correct rigorous definition. Okay, so keep that in mind. So now let's try to see an example that what are we going to do with this differential forms. That is, what does these differential forms actually do? So let's first take a very simple example, and what we want to compute is the following. Let's say I give you a quantity like this, some 2 till x1 plus 3 dx1, like this, and I want you to compute what is dx1 2 times dx1 plus 3 times dx1. This is pretty easy. You just multiply them as we have seen before. You take the 2 out according to the second property that was introduced in the definition, and you have this dx1, then the partial of dx1 like this. You have 3 dx1 partial of dx2, and from the definition that we saw a few minutes ago over here, this one, you can immediately recognize that this is just 1 and this is also 1, so you have 2 plus 3, which is equals to 5. And if you look closely, you will actually understand the fact that these differential one forms are just measuring the projections of these vectors on the cotangent space axes. That's one way to think of it. Or you can also say in another way that these differential forms are actually giving you the projection along the axes of this tangent space. In fact, that is more correct way to think of it. So these differential forms or differential one forms gives you a a projection on the basis of the tangent vectors. Now similarly you can also try to compute another quantity. Let's say this is our example 2dx minus 3dy plus 5dz. Again remember these are forms, okay, differential one forms, and I want you to compute the quantity, this guy. And again, if you understand that this dx will only produce a non-zero thing when it is acted upon this guy, and all the other elements will be zero. This is just a one-line computation, just like dot product that you see in your ordinary vector analysis. This is just minus 2, minus 9, and then we have 5 and minus 4, so it should be minus 20, right? So this is just minus 31. That's it. So why are we even bothering with these things? Well, we are bothering with these things because first of all we want to know what is the geometrical interpretation of a total differential. I mean, we have defined one form, and from there we can also go to 2 form, 3 forms, and so on, and we will define something new type of product that is called a wedge product that will actually help us in achieving our goal of understanding how volumes, areas, these are all antisymmetric products and all that, but we'll come to that a bit later. First we want to use this one form tool to gain some better understanding of what we have learned in our calculus course so far. So I want to give you a slight review on the total differential, because most often in calculus courses we say differential, there is a differential, let's say dx, dy, dz, but we don't actually give a geometrical interpretation of what the differential measures, and that's a very important thing to do, and for that we need this one form language. So what is a total differential? If you have a multivariable function f of x, y, let's say z, then the total differential is just df given by the partial derivative of f with respect to x. And remember, from calculus point of view, this is just a differential, right? Dx, some infinitesimal change and stuff. So this is given by this thing. Now what about the one form language? How does one form defines a differential? Because we want to see what this one form language is actually good for, right? So now we define the differential or the total differential in terms of one form language. So this is on the calculus language or calculus language. Now we want to see the definition in the form language. So the definition for a total differential or a differential, if you want to call it, will be the following. So the definition is that let there be some function f on the manifold, that means it takes input from the manifolds, the points, and it maps them to a real number. Then the differential df of the function f is defined as, or defined to be, in whatever way you want to call it, is defined as the one form on the manifold Rn such that for all vectors VP, let's say, that means we are taking some point P and this vector is on the tangent space, we have the following to be true. This means that df acting upon the vector on a tangent space will give us the same output of this guy over here, which is a linear functional. That means if you are taking a function, you are doing some vector operation on it with VP and you are getting a number, right? And differential form also does the same thing. It takes a tangent vector, the one form itself is a member of the cotangent space or the dual space, and it gives you a real number. So this is what is actually happening over here. And if you recall from the past lectures that this was nothing but the directional derivative, so this guy was just the directional derivative on that manifold, or so to say on that point of that manifold. So this was written as ddt of f of p plus t vp, and we want to compute at t equals to 0. That means at some certain point, right? And in our past lecture we saw that this was nothing but df, let's say this is dx1 v1 df x2 v2 df x3 v3, where vp was written as v1 v2 and v3, like this, right? Now before we proceed, we want to see another thing. That means we want to see how we can start from here, the directional derivative notation, and we can end up over here. Okay, so for that we want to write VP, that was written like this. It can also be written as this, right, where e's are the basis vectors on that Cartesian coordinate. So v2 e2 v3 e3, but recall that e of I was given by this guy, right? So we can finally write it as dxi v2 dx2, sorry, not I, it should be 1 v3 del x del 3. Now we use this, that means we use the fact that these ei's are equals to this, and we also use the fact that dx1 of partial of 1 is just 1, and if we act with dx1 on vp, it should only give me v1, right, because it's measuring the projection along the e1 axis. That's what differential one form do to a vector from a tangent space. Similarly, dx of vp would give me v2. Similarly, dx of vp would give me, dx of 3 of vp would give me just v3, right? So instead of this v1, v2 and v3, I can now substitute this fellas. So let's try to do that. So let's call this 1. So from equation 1 we can write this as df dx1, and v1 can be written as this dx 1 vp, then df of dx2 can be written as dx2 vp. This means that dx1 is acting on vp. So please don't confuse this with ordinary multiplication. Even though the notation might be a little bit confusing, this doesn't mean they are ordinarily multiplying with each other. They are like operators and they are acting on those vectors and stuff. So final term would be dx3 vp, right? Now, since these are partial derivatives, it will give you some type of function, or if you want to evaluate it at a point, it will give you some number, and the only operator type of thing is these differential forms, and the operand, that means the guy who's getting operated, are these vectors, right? So in that sense, you can write this as dfx1 dx1 df2 dx2, and this term, this whole thing operating on this vector v of p, right? And comparing the left hand side with the right hand side should convince you that so now comparing left hand side with right hand side, one can conclude that the differential is given by this one form. Again, this differential is just one form, and this expression verifies that thing, right? Now the question is, what does this differential form actually mean? What does it mean geometrically? Well, let's try to look at the definition again. If you see this definition, you can see that on the left hand side we are talking about this differential one form acting on some vector, but on the right hand side this is equivalent to a directional derivative, right? So from there we can conclude that this differential form on a manifold, let's say this is my manifold, let's say I have some point and I want to see how this function changes, because on calculus we say that how this function changes on multiple axes. Let's say this is our coordinate axis, x1, x2 and x3, like this, and we want to measure the change in some direction, because on the right hand side we had a directional derivative definition, right? So at this point you can draw a tangent space like this, and what this differential form tells you is that how that direction you want to move, that means the choice of the direction vector over here, that means this blue line, so this is the vector along which you want to measure the rate of change. This gives out a number, this differential form, it actually gives you a number that is the rise of this plane, that means the tangent plane, to the graph of the function as one moves from this initial starting point to the end point. So don't confuse it, don't confuse this arrow with this manifold, because the manifold will have something like this, like for example it's going down. However, you can see that the tangent is a bit away from this point over here. So this differential form df actually tells you or gives you a number, let's say gives you a number that measures the rise along the direction rise of the tangent space along the direction of the vector t, or so to say the vector of interest. The vector, let's say, since this in this picture I have written it as S and E, so I'll just call it as C. This is the geometrical meaning of this total differential. And there is another way to see it as well. What you can do is that you can call this point S. You can call this point as the point where you have this thing, okay, and then you can have some derivatives that actually gives you the projections along the lines of x and y's, or so to say x1 and y1. So instead of y0 you could write, let's say, x1 x2, and you could measure these slopes. And finally what you want to do is that you want to see the difference of the quantity that will be given by x0, let's say x1 x0a, x2 0b, like this, minus t of x1 0 comma x2 0. That means you are just ultimately measuring the difference between two tangent vectors, and you can think of this as at this point, that is the point E, you can draw another tangent vector like this, okay. Then you can translate it back, and a two-dimensional picture would look something like this. What you are doing is that you are only measuring this difference, call it by delta t and denoted with this. So this is a more vector type of, or so to say, draw based approach, but in differential one form language these things are immanent. So to sum up, what we have learned is that these differential one forms are something that comes up with 1D, that is related with the infinitesimal changes, as we saw in the total differential discussion. And what it does is that it takes something from the tangent space and it spits out a number. Alright, so in the next lectures we are going to see more differential forms, like 2 forms and 3 forms, and we will define a new type of product that is called a wedge product, and from there we will see how the Jacobians arise very naturally when we do a coordinate transformation of an area or a volume, and how areas and volume, they will even have signs that are pretty much neglected in any calculus courses. But when we use these differential forms, we have to take them under consideration and all that. So this will be it for today, and I'll see you guys on the next lecture. Thank you.